Thanks for having me here and coming and listening. It's been fun. So the last ingredient that I haven't discussed yet is this intermittent pressure. So in order to set the stage, let's sort of recap our whole train of logic, which is sort of like this iteration that we're setting up. So, all right, what happens first? We set up this C alpha iteration, and we found that it was limited to alpha equals 1/4. And we also talked a little bit on the first day about sort of the physical background of turbulence and the phenomenological theories and the numerics and experiments a little bit. And based on these, we can sort of reasonably expect that this L3-based Bessov space is at least well motivated to build solutions in instead of C alpha. All right, so we're going to work in L3. So now we set up this, L3 Nash iteration instead. And the main difference with the C alpha iteration is that we've smeared out the frequencies. So and the other main difference was that this had the effect of rebalancing the sizes of the R's and the phi's, right? That was what saved the day and told us that we could hope for B1/3 minus 3 infinity as sort of the upper limit of this iteration. All right, but we smeared out the frequencies, and as a consequence, we lost some frequency separation that we used to have. And so what we did is we replaced frequency separation with combined or joint space-time and frequency support separation. All right, this was the inspiration for the wavelet-inspired schemes. All right, so then when we were setting up an iteration which is taking into account this sort of thing, we changed some of the names of the variables. So we relabeled some of the frequencies. So we used to have this parameter and the Q, A to the B to the Q. We left that one alone, but we sent the old lambda Q plus 1, we sent that to lambda Q plus n bar, where n bar was large. All right, so let's just I'll put those definitions over here too, so we can leave this board up with all of our main things. So we have lambda Q, our frequency parameter. We have delta Q equals lambda Q to the minus 2 beta. That was our amplitude parameter. And we had RQ, which was the intermittency parameter. It was determined by that Goldilocks ratio. And if you compute this out, this is basically the same as taking the full quotient of the midpoint frequency and the endpoint frequency. All right. And I guess one of the other things that we found here was that we had errors at all frequencies. All right, so when you have errors at all frequencies, what should the inductive setup look like? Well, going to get a bit uglier. So on the right-hand side, instead of just a single error term, we have a whole host of error terms. Are QK, I guess, inside of the divergence. And the idea of this thing was that it oscillated at frequencies less than or equal to 1. All right. Now, here's the point where we're going to put in the intermittent pressure. And so let me explain why. Why is the intermittent pressure brought to here? All right, so I'm going to call the intermittent pressure pi. And the idea of pi is that it measures deviations from mean, i.e. it measures intermittence. All right, now there's a few things that we're going to need about this intermittent pressure. And the first one is related to the Reynolds stress, which, all right, so what happened with the Reynolds stress? So when we started, we did this simple example of the Reynolds stress, which was a negative function in the top left component. And we canceled this with something which looked like the square root of r cubed times something hyphen lambda something y. I guess at the beginning it was lambda t plus 1. Now, in general, I'm not going to have Reynolds stresses with just the top left component. I'm going to have Reynolds stresses which are negative definite symmetric tensors. Or sorry, what do I want to say? What I want to say is that this cancellation mechanism, it required R cubed to be symmetric and negative. And this was just the simplest example of symmetric negative definite. All right, but these are cubes. I mean, they're not a priori going to be negative definite. And so in order to make them negative definite, I'm going to replace R cubed with R cubed minus I cubed times the identity, where this is a positive scalar function. And if I subtract something on the diagonal, which is large enough, I'll get something negative definite. And I'm actually going to do this in all the components of the right-hand side. All right. And what am I going to need in order to ensure that this is negative definite? I'll need I cubed k greater or equal to, let's say, twice R cubed. All right, I don't want to make it too big though, so let's also suppose that its L3 Hz norm is the same size as the L3 Hz norm of the Reynolds stress, which in this setting was or is delta A plus n bar. So why is that number? It's because A equals Q, we get delta Q plus n bar, which is the analog of the old delta Q plus 1 that we were using before. Okay. Now, over here, I guess. All right. I'm feeling a little bit ambitious though about my ability to construct this pi q case. Let's impose some other progress. I'm also going to impose that not only does IQK dominate this Reynolds stress, it dominates the derivatives pointwise in space. And the multiplicative factor that I should get every time I take a derivative is the frequency. These things oscillate at frequency at most length. And since I'm feeling, I guess, even more ambitious, I'm also going to say that this dominates derivatives of pi q k itself. All right, so this has to be a pretty carefully constructed function if it satisfies this property that every time I take a derivative, it gets bigger by a multiplicative factor of frequency. All right. So this is the first thing we're going to impose about pi. All right. So pointless. All right. So we've said something about pi and r, or the Reynolds stress. What about pi and phi? Is there some relationship between the size of these things? Well, let's look at the Euler-Reynolds oscillation error, which is now going to be divergence. All right, so how should I do this? Let's leave myself some room. And remember that WQ plus 1 is designed to correct only the lowest bin in this menagerie of error terms. So this corrects RQQ and also IQQ, which I guess I haven't written yet. So let's write that. I just want to remember our last local energy in quality. So I'm also going to put the giant sum on the right hand side over here. And what's going inside this giant sum? Well, a whole host of phi's at different frequencies. And there will also be the generalization of what we used to have before, which was RQ times u. And what I'm going to put here now is r cubed k minus pi cubed k identity times u k minus n bar plus 1. All right, so the point of all these things that have k's dependent on them is that they all oscillate at frequencies less than or equal to lambda k. So everything that has frequency lambda k is grouped together on the right-hand side. All right, so if WQ plus 1 is correcting phi QQ, this means that this WQ plus 1 phi ought to be the cube root of minus phi QQ times one of these bundles that we defined yesterday. All right, and these bundles obeyed estimates which came from the width of the frequency support and Bernstein. So the frequency support was lambda q plus n bar over 2 up to lambda q plus n bar, which when we wrote out the LP estimates, we got r cubed, the 2 over p minus 2 over 3 and L3. All right, so this bundle was normalized in L3. I plug in p equals 3 and I get 1. And that's what enacts the cancellation of pi. All right. So what's happening now in the Euler-Reynolds oscillation? So this is when I see RQQ minus pi QQ identity. That's what I'm trying to get rid of. And what I'm also going to see is this tensor product of this one with itself, and also the tensor product of this one with itself. And why did I close the parentheses without writing the cross terms? It's because I choose the bundles for the phi and the r bits to have disjoint support. So I don't get any cross terms. All right. And okay. Let's add something times the Reynolds bundle. And I want to figure out what that something is. And what should it be? Well, all right, so let's forget about the fact that these are tensors. Let's assume that everything's a scalar. W tensor W with phi is going to give me the mean of this bundle squared times phi QQ with 2/3 plus identity minus the mean of this bundle squared times phi QQ with 2/3. This is all from WQ plus 1 phi. And the point is that this is low frequency. And it's popped up in the Euler-Reynolds oscillation error because when I square this thing, or when I tensor it with itself, I'm going to get some low frequencies appearing. So in order to get rid of these low frequencies, my Reynolds corrector ought to have RQQ minus pi QQ plus pi QQ to the 2/3. Times whatever the mean of this bundle squared is. And the size of this is something that I can read off of my estimates. It's RQ, I plug in P equals 2, and I square. So I get RQ. And so I'm going to put normalization in here. RQ to the 2/3. So that my Reynolds bundle helps me get rid of this pi QQ. I guess I put it with I should put it with 1/2. And I guess I should change the sign so they cancel. So minus plus. This is Reynolds bundle squared plus whatever else. All right. Why did I write out this long computation? It's because it tells me what the scaling relationship is between the pi and pi. These are both appearing in the same coefficient, and so I expect them to have the same size. All right. All right, so the second thing I'm going to impose on my intermittent pressure is that continued. Is that when I take derivatives of this phi, what's the scaling here? So phi to the 2/3 times r to the 2/3 is like a pi. So phi to the first power is like a pi to the 3/2 times RQ inverse. And when I take derivatives, I spit out the frequency factor. All right, so this is the second thing that I'm going to impose upon my intermittent pressure. Or I'll construct this so that this is real. All right, so we've used this intermittent pressure to dominate the R. We've used it to dominate the phi. What's left in this equation is the velocity u, and so we're going to use it to dominate the velocity as well. All right, so if you do a bit of arithmetic sort of in the similar spirit as what we just did, you find that the right scaling relationship is the following. So if I want to dominate the velocity, which has maximum frequency lambda q, I should use the pi, which oscillates at frequency lambda q, and the correct scaling is pi to the 1/2 because pressure scales like velocity squared. So pi to the 1/2, and then we're going to decorate this with some numbers, which if you write out the arithmetic, you'll see that this is the right scale. All right. So we're just using pi now to unify all of the estimates of all the things that appear in the relaxed system in this fashion. And the last thing that we should notice about this pi is the following. So if I look at this velocity field, it has units of 1 over time, which sort of tells me that the size of this gradient should be related to the cost of the derivative along the flow of this field. Cost of dt plus u dot alpha.
Why is that?
Because if I set up the transport equation with this velocity field, and I ask on what time scale, or I mean, how do I get stability estimates on the flow of that vector field? I need to know the size of the gradient of the vector field. Wrong.
Okay.
Okay. Which tells me then that the cost of this derivative is exactly equal to the right-hand side of this thing, if I just ignore the extra variables that I've included. All right.
Can I interrupt for a second?
Yeah.
I'm a little lost about what is given and what you construct. So in 2 and 3,
IQQ is given. It's part of the inductive setup.
IQ is this given. Okay. And you, okay.
I may have to construct the next one later.
So in 2 and 3, you're constructing everything.
I'm not constructing anything. I'm telling you what the inductive assumptions are. And
Okay.
all right. Thank you for making me clarify. All right. So I can now finally state what some version of the real inductive bounds that we actually use in the picture. So the first thing is we say that the size of this is delta Q plus M bar. And I'm just going to do it for pi QQ, and you can figure out how to extrapolate to the other values of K. The second thing, which was on my list of things that I imposed about pi, or that I assumed inductively, was, well, I guess I didn't exactly list this, but how big should derivatives of pi QQ be, where I have both space derivatives and derivatives in the direction dpq, which I'm using as a shorthand for this this material derivative along this velocity field. Let's call this number tau q inverse. And I want to emphasize that this tau q inverse is a function of time and space, because it depends on this pi, which is a function of time and space. When I write down this bound, I'm not going to put I'm going to suppress the dependence of this tau on time and space. And part of the reason I'm doing this is because it makes the estimates look neater. And if you've run a few of these iterations before, this estimate should look familiar.
Norms?
Say again?
Are these norms? You have a double
Pointwise.
single
Pointwise. So I evaluated in TX, and I have the left-hand side as well, but right. Sorry, 3 hands. Thank you. All right. I have similar bounds for the R3Q. This is what I expect based on these considerations about the cost of material and this. Okay, so let's do the one Y. So we said the scaling here was 3 halves with RQ. And then we have lambda Q and and last but not least, we have our velocity bound, and I'll throw the third derivatives in there as well. So this is u minus m plus 1. And I'm going to have, well, I guess this is really, it's 1 tau Q inverse from here. It's lambda Q's from the spatial derivatives, 4 taus from the material derivatives. All right. So these are the actual inductive bounds that we use. We unify everything in terms of this intermittent pressure. And it's a bit more convenient actually than trying to keep track of separate estimates for everybody. Because all I'm really keeping track of now is point-wise sizes of these derivatives, and then just one L3 half norm on pi. Okay, now I'm going to add one more inductive assumption. And this inductive assumption is as follows. So if I take the intermittent pressure at frequency lambda Q, and I mollify it at length scale lambda Q prime inverse, which I'm assuming is bigger than lambda Q inverse. So if I go backwards to an old frequency, what should I expect to find? I should expect to find the old pressure, pi Q prime, with a rescaling factor, which is this one right here. All right, so what is this saying heuristically? It's saying if I take a function which is intermittent, so it has lots of peaks of various thicknesses, and I average out at a length scale, which is rather broad, I'm going to kill a bunch of the peaks. And what I get back is the old measurement of intermittency with a rescaling factor. And this is consistent with this bound here, because if we take beta close to 1/3, then this is kind of morally speaking like lambda Q to the minus 2/3. So in order to upgrade from step to step, I should be multiplying by a ratio of lambdas to the 2/3. That's exactly what this is doing here. This is consistent with this bound right there.
This I is not positive, it's positive.
Sure, I mean it is positive, but I mean it has peaks and whatnot. All right, so let me say something about how, or heuristics at least, about how we construct this pi.
You are saying that you are remembering everything through pressure, but in fact, you need also to know the supports of everything, right?
Yeah.
In the real direction, right? So you.
Yeah. Yeah, I mean, support information is kind of built into all these estimates. Okay. Because it tells me, I mean, if I know where pi is large and I have this pointwise estimate, I know where all the things on the left side are large. All right, so what's the heuristic here? Well, forget all the derivatives. They're just sort of clouding the idea of this. At least at the base level, what I'm going to need in order for these inequalities to be true is for pi QQ to be the absolute value of RQQ. That's how I'll get this. Plus RQ to the 2/3 absolute value of phi QQ to the 2/3. That's how I'll get this. Plus, what's the scaling that's going to give me this? Well, I guess I sort of hit it inside the tau. But if you expand this out, the scaling that you get is 1 to the q to the -2 RQ squared gradient into q minus 10 r plus 1 squared. All right, this is the simplest possible definition that I can imagine, which will give me these estimates, at least if I don't take any derivatives. All right, but let's think about this another way. So let's convolve pi QQ with a bunch of currents. So identity minus lambda q inverse. So I subtract, meaning I also have to add. And I'm also going to now subtract lambda q minus 1 inverse. And now I have to add it back. All right, so I'm just adding and subtracting a couple things. And now I'm going to group these together like this. All right. So this pi QQ, it oscillates at frequency lambda q. So if I'm clever with choosing my modifier and I maybe change the length scale a little bit, I can get that identity minus this modifier involved with pi is going to be, morally speaking, very negative. It's like saying if I take a function with compactly supported frequencies and I modify the scale which is slightly outside the compact supported frequencies, I get back the original function. All right, so up to negligible errors and maybe slight adjustments in this length scale. This first term is 0. The second term is a difference of modifiers. So I'm again going to cheat a little bit and just think about this as a little Paley projector, where I'm only isolating the frequencies in between lambda q minus 1 and that. And the last term is exactly what I have from over here, which is being evaluated with lambda q minus 1, which means this is pi q minus 1 q minus 1 with the rescaling. All right. So the idea of this pi is that it's something which is high frequency plus old rescaled pies. It's as if we've done a frequency or wavelet decomposition of this pi, and we said that it has the highest shell plus all the lower shells. And by this inductive assumption, all the lower shells just jump back to one of the old pies. All right, so the question now, we'll see how much time I have to answer these, but the questions are, why is this the right heuristic? So why this heuristic? And how do I construct this thing? All right. And I guess there's one thing, one stone left unturned, which is that I also put something else in this empty space that I left. And I'm not sure if we'll have time to see why it should be there, but let's just put it there for the sake of accuracy. All right. Let's answer this first question. Why is this the heuristic that I'm going to employ? So let's consider some error. Let's consider the relaxed local energy inequality. The oscillation error. So the nonlinear error that arises from taking the interaction of W's. And let's go back to our simplification of just ignoring any coupling between the phi's and the r's, and let's just look at phi. All right, the idea with these nonlinear errors was that when you add these two things together, all that's left over is the gradient of the phi and the projection off of the mean of this high frequency bundle B. And I'm just going to write cubed because I'm too lazy to remember that these are vector fields. So think of them as just scalars. All right, so what frequencies are in here? There's lambda q plus n bar over 2, so lambda q plus n bar. Which means when I define a current error or a phi, a new phi error, I have to put this thing into divergence form. And I'm going to skip all the lowest shells from this and just focus on the last shell. All right. This is a new phi. We'll just call this, it phi. Wait, I haven't put it in the divergence form. I haven't put it in divergence form yet. Right, in order to turn these into errors, I have to put them in divergence form. All right. We'll call this phi. All right, so my first claim is that phi, morally speaking, is equal to letting this Fourier multiplier or convolution operator or whatever it is, letting it fall on the high frequency thing. And then I'll have some other order terms, which for the moment, I'm just going to ignore. All right, so let's just focus on sort of the leading order term of this thing, which is this. This is a new phi, which means that someday it's going to have to obey an estimate like this. And so I have to construct a new pi sub phi to help me control this phi pointless. That's my inductive assumption. And when I create a new error term, I have to also create the pressure, the associated pressure, which will allow me to have this estimate. All right. I'm going to race up to here. All right, what happens if I just take an absolute value of this? That's the silliest possible thing that I could do. So this phi, this new phi is less than the absolute value of this. And now I'm going to take the absolute value of this, but I'm going to split it into the mean. Plus the projection off the mean. All right. What is this first term by my inductive assumption? So one is less than pi q cubed to the 3/2 times lambda q coming from this gradient. And our q inverse times the mean of this guy. And the mean, when I project onto the highest frequency and I invert the divergence, the L3 norm of this thing is 1. And so this is 1 over lambda q. And 2, the second term, has projection off of the mean of the high frequency object. So 2 high frequency. And this is why I said that the heuristic for the pi is something which is high frequency plus old rescaled pi's. This is just an old rescaled pi. All right. So this is the heuristic behind this inductive bound, which we propagate by ensuring that all of the later pies remember something about the old pies. All right. So I only have one more thing that I want to say quickly, and then more. Okay. So the last thing I want to say is about what happens when we try and throw this new pressure. So let's call this thing this is the new pressure that I need to add into the system. So this is the pi phi that I have to add in order to help myself dominate this error cone phi. So what happens when we add pi phi into the system? All right. Well, in the Euler-Reynolds bit, I'm going to have to take the divergence of this new pi, but I can easily just balance it out with the pressure on the left-hand side. So Euler-Reynolds system, I just add pi phi, or I guess gradients pi phi, to both sides. No trouble there. What about in the relaxed local energy equality? There's no pi's on the left-hand side of the relaxed local energy equality. So there's nowhere to just hide it on the left-hand side, which means that I have to just add and subtract. What do I have to add and subtract? I have to add and subtract. Let's just focus on this term here, which has the material derivative of so material derivative. The one that I add will slot nicely right in here where I want it to be. And then the other one, I just have to estimate as a new phi error. So I have to estimate the divergence inverse of projection off the mean of this thing that I added. And let's give this a name. I'm going to call this phi pi phi. It's a new phi error, which came from estimating the pi from a slightly less new phi error. Slightly less new pi. And this is bad because this looks like a loop, right? It looks like I make a phi error, I make a pressure, I have to estimate this term. It makes a new phi error, and now I have to make a new pressure, and I look like I'm stuck. So all right. But what can save me? The only thing that can save me is that I can hope that this new phi is actually secretly dominated by one of these old rescale pies, which is already present in my system. I pulled rescaled pi, which I already have access to from the induction, which is already there by induction. When I made the old pi, I made sure to include a little bit of it to save for this later stage when I know I'm going to need it. And it turns out if you do this estimate, this is actually sharp in v1/3 minus 3⁵. And I don't have time to make the estimate, but it's actually not that long. But this is a minor miracle in some sense because we did all this work, and at every step, my hand felt forced. I'm forced to use L3. I'm forced to use a wavelet iteration. I'm forced to use this silly pressure to make this tensor negative definite. Now the pressure shows up over here. Now I have to estimate it. And I get to the end, and I look at this estimate, and it looks like I might have a loop, but luckily there's no loop. And yeah, I'll stop there and